it's recording. Okay, so it's my absolute pleasure to welcome Gustavo Bruzual to give the first talk after the summer break in our Commission J1. So those of you working on stellar like spectral energy distributions in galaxies, I think Gustavo needs no introduction whatsoever, but in any case, let's give a brief one. So Gustavo has been working for a long time on the business of population synthesis of stellar populations. He's an investigador, a researcher at the Centro de Radioastronomía y Astrofísica, so a Center for Astrophysics of the National University of Mexico in Morelia. Before that, he was, for many years, he was working at the CIDA, the Center for Astrophysics in Venezuela, where he was the director for many years. Years back, he got his PhD at the University of California, Berkeley, on the analysis of stellar populations. He's, I would say, one of the pioneers of applying these types of methods, which all started with people like Beatrice Tinsley and Hiram Spinrad and Sandy Faber and Gustavo himself. And then after that, it developed into a number of models, of which you are mostly familiar with the Charlotte-Bruzual or Bruzual-Charlotte models that have been around for many years. So it's an absolute pleasure to have him giving this talk. I have to mention that the Bruzual-Charlotte 2003 is one of the top cited articles in astrophysics. It's at the top highest level. So basically at the same level of papers such as the one on NFW profiles, Navarro, Frank, and White. So I think it's very nice to have the opportunity, the pleasure to have Gustavo give us a talk. And he's going to give, there's this generic talk, but I think it's going to be very interesting material of new developments using a collage of spectral libraries to model the stellar populations of single and binary stars. So thanks so much, Gustavo, and the floor is yours.
Thank you, Ignacio. I apologize if some of the context I will be talking you're already very familiar with it, but I will introduce some of the things that we use so that people will profit from my talk. In most of the work that I will be talking here has been done in collaboration with Stephen Charlotte and other collaborators that I will be mentioning during my talk. And this is mostly an updating and an upgrading of our previous work, like Ignacio mentioned, the 2003 work, which that is the standard setup, even though all the ingredients that we are using now are really new, and they keep changing all the time. Essentially, we distribute new models, even if we don't have new publications for every upgrade. The latest stable upgrade is this by Platt et al. 2019 that we call CMB models or CB19 also. So you will hear that work alone. So what is this stellar population synthesis? It's more or less the art of discovering how many stars of each kind are there in a galaxy or star cluster from its integrated light, either the photometry or the spectral energy distribution, without observing or counting the individual stars. This sounds a feasible thing, given the amount of information that we have now about the extragalactic or even galactic objects. I want to spend a little bit of time talking about the historical reasons why people got into population synthesis. This is an update letter from 1960 in which Minkowski reported the higher redshift at the time for this galaxy, 3C 295, which is a radio source. You can see this little point here. He could measure the redshift at 0.461, which was the highest redshift at the time, 4.5 hours exposure, 9 hours exposure. And it's very interesting that they already talk about photometric redshift. So we think that we are coming with new things all the time, but people 60 more years ago already have this. And also they favor what they say exploding universe and the need for more data. So this was one of the triggering kind of work that people were doing. So Sandage in 61, 1 year later, was asking himself how much brighter this galaxy is than a local elliptical. If they were aware, people were aware that stars are evolving, so galaxies should be brighter, but they didn't know how much. So these people already knew that the evolution of the stellar content of galaxy is very important to be able to solve the Hubble diagram, the MC relation. The evolution of the elliptical AC0 galaxies is the most important of the unsolved problems that are now blocking the solution of the cosmological problem in 1960. And they thought that it might be very difficult to find the data with sufficient precision to correct the observed magnitudes for evolution. So that was 40 or 60 years ago. So, and they already have very good ideas. That is essentially what we keep doing now. In 57, this Morgan and Mayall already, they suggested that the stellar content of the Virgo elliptical and zero galaxies will be very similar to the all-star clusters in our galaxy, like NGC 188 and M67, which I show here in the right. And they use very simple arguments, assuming that this galaxy 3C295 forming a single burst or a simple stellar population with a similar metallicity to this cluster, Sandage could compute more or less an order of magnitude of the change of brightness of the cluster M67 to go back to evolve into NGC 188, essentially how much one evolved from the blue to the yellow. And he made some assumptions that after a few iterations, he concluded that omega will be 0.4, that the light travel time will be 0.3 times the age of the universe, and the evolutionary correction was about 0.4 magnitudes. Now, modern values are not very far from this. I say omega now we think is 1, but the light travel time was very close, and the evolutionary correction wasn't so bad given these very rough approximations. So the whole business of doing it correctly came with this motivation. I am not as old as these people, but when I came to Berkeley, Minkowski was still around. And in Berkeley, there was a hot topic to find out, to work about the galaxy evolution and spectral evolution. And that was why my advisor, Hiram Spinrad, got me into this business. At the time, I started working on this in around 1975, which is like 15 years after Minkowski's discovery, but this was still the highest redshift galaxy. So the universe has grown a lot in the meantime. So what we need for doing these evolutionary synthesis models, as all you know, we need stellar evolutionary tracks or isochron, the stellar spectra. We must know how many stars are there of each mass, temperature, and luminosity, which essentially is the initial mass function at the time 0. And a computer code that will put everything together and will give us the evolution in time of the integrated spectra, or SED, of the stellar population, and the physical properties of the population, the mass in stars, in gas, in remnants, the rate at which different remnants appear, the mass luminosity ratio, etc. And in general, we compute the chemical evolution of the population independently of the spectral evolution, because otherwise it gets complicated. For the most of the work I will talking here, I will be using what we call the parsec tracks, which are some tracks that evolve from the Padova tracks and are base in Trieste with people in Padua as well. These tracks describe the evolution of non-rotating single stars. Then they don't consider mass transfer between stars in binary pairs. So it's simple models for simple synthesis model for single stars. In this case, later on I will speak of models with binary stars. This improved over previous versions of the tracks and for the Padova group in the treatment of the Hados, the mass loss rate. For the most massive stars are long way for a stronger stellar wind and lower metallicities. They include evolution of massive stars through the Wolf rate phase and are available for a large variety of chemical mixes. I show here a table. This is a subset of the ones they have available. Here we have 16 different values of Z that we have implemented in the CV19 models. On the left, you see a typical HR diagrams of these sets of tracks. They go in mass from 0.1 to 600 solar masses. There are about 26,000 points for each metallicity. The diagrams on the right show the details of the high mass stars. So you see, it's a lot of information about the evolutionary tracks. Also, we have the work by Marigo to take into account the TPAGB, which is put together into the parsec tracks. So it's a the leading researcher in the parsec tracks is Bressan. Even the paper is by Chen and collaborators. So this is a very complete thing. But as you can see, we have a lot of points for which we have to find a spectrum. For instance, for the 008 metallicity, we have the high masses above 6 is 35 masses plus 70 solar masses below 6. So it's a total of 105 evolutionary tracks for which we have 26,000 points in the HR diagram. This guarantees a very smooth evolution of the population and the spectrum, which is very good. In the past, if you go back to the original models that we work, I mean, the tracks were very coarse and we have jumps. When we evolve in time, we couldn't follow it very smoothly. Now, thanks to this very high resolution in mass and in time steps, we can have a very nice evolution. The problem is how to fill these diagrams with the spectra. Here on the top is this, you see the HR diagram. Here is the log-G TEF diagram for the same set of tracks, which is solar here. And on the right, what I put is more or less with these polygons is just the range of parameters that we can cover with the main stellar libraries that are around, like Miles, Tilasti, Martins. And you see that each library covers a different part of the diagram, and there are some regions of the diagrams that are not covered at all. So this is what I call more or less like a collage, because we have to, if we want to make a model that can be evolved to long redshifts and answer Minkowski's questions, we need to put everything together in a self-consistent way. So we have to compromise, and ideally, we would like to have a single spectral library to avoid systematic effects, but such a thing is not available for the moment in all the wavelength range. As we will see later, in different wavelength ranges, we can be more self-consistent. Here I have a table with a summary of what is used in these CV19 models. So you can see it's a lot of things. In the ultraviolet, we use all these libraries because each of them has different, as we saw here, when we hot temperature, we need many either models. Most of them are models. There are essentially no observations in the ultraviolet range. Also, in the visible, we can use Miles in the US or X-Shooter. There are many libraries. And the infrared is that there are these libraries, right? So in total, we can have very good, a very high sampling in the spectra. Recently, we have around 46,000 points in sampling. Another point, as you can see here, the wavelength range is different. So you have to put them together. The resolution is different for each library. So you make a lot of operations in this spectra to try to put it in a consistent way. And also the sampling is not trivial. We are using this routine by Karnal, which is called SpectRes, which essentially tries to put in the same sampling a spectra of very different resolution. And that has been successful somehow. So I show here some example of this resample spectra using this Karnal routine. On top, these are the later et al. 2010 basic spectra. So you see very nice looking spectralists for these temperatures going from 20,000 to 60,000 K, and the same spectra, the same range for the T-lasting models. So you see a big difference because in the lighter models, we are taking into account the expansion of the stellar atmosphere. So if we don't use this, you will never get the P Cygni profiles. So I will show some basic results from these models. So the basic thing, the first thing you get is a evolving spectra that goes from the UV to the very far infrared, from the extreme UV to the very far infrared, that evolves in time. This is what we have been doing for a long time. Now we have more and more resolution. I will show the same spectrum. This is from almost 0 to infinite. Now I go here from a few angstroms to a few microns, and below 5,000 angstroms. So you see that the spectra have a lot of information, which we want to use, or people want to use. One of the first applications of this was done by Adel Platt, and that's why the CV19 models are introduced in this paper and are called Platt et al. Even we call the models themselves CV19. So in this paper, she did a lot of work and diagnostic diagrams using the ionizing radiation from these models and the cloudy code. And she has many, you are interested, many diagrams like this explaining different properties of the emission lines in galaxies, depending on the ionizing radiation that escapes from these kind of galaxies. Igual, the evolution of the helium-2 line, which is very important. And again, color diagnostic diagrams for several metallicities that are available in these models. Then there is an interesting work that was performed by IRyA Warford and all these people here, studying this galaxy, which have very good data from the Hubble telescope. And you can see here is a comparison of the models I just introduced. The observation is in blue, the model is in red, yellow, orange, I guess. And you can see that most of the features match quite well. Yeah. In this particular fit, IRyA needed to have these very high masses. Models with this very high upper mass, 300 solar mass, which is one of the important results of this paper, which is the dominant role of very massive stars. This BMS thing is now is fashionable. People are finding evidence that these very massive stars are present in galaxies. So I will show you here a little bit of what we predict for this this model, the models that we gave IRyA to do this study essentially. So we can discriminate by upper mass from 600, 300, 100. You can see in blue, red, green at different ages in the wavelength range that IRyA was interested. So you see there is a very strong evolution in very short time. The 2 million years, 2.5, 3, 3.5. So you can really point out with sort of very high precision the age of the stellar population because the stars disappear very quickly. This one was from 1100 to 1300. Here is 1700 to 1500. And again, you see that the evolution is quite fast. The same here from 1500 to 1700. I put this in 3 different plots because, I mean, you don't see anything if you put everything together. But this is the range that IRyA was studying. The only thing, she has the flat spectrum and we keep it in the natural units. So this, when IRyA, when she does the fit, she can conclude that it's much better, 2.4 is better than the other ages. Even if it sounds sort of I don't know, people, when we work in population synthesis, we are not used to this precision. 2.2 being different of 2.4 or 2.3, but since the evolution from, you can see here, the evolution from 2 to 3 is quite strong. She could point out that the best age is 2.4 using some kind of fitting algorithm, which is interesting. So now we can ask ourselves the question, what stars are present there? What are we looking at in this kind of galaxies? We should remember that Wolf-Rayet stars are important. In a cluster of 1 million solar mass, we expect around 100 Wolf-Rayet stars. So here what we did is we took the best fit from IRyA, which is 2.4 million years, and we check what stars are present in this population and are dominating the total luminosity. In green, we show the main sequence, and in pink or purple is the Wolf-Rayet contribution. So still the main sequence is much more important. The contribution of only in some features, like here it can be 20% in these emission lines, in a little bit about 20% from the Wolf-Rayet. So it depends what you are studying, how relevant the contribution of the Wolf-Rayet stars is. But this is important to have them present. This is again, this was the different wavelength range. You see again the dependence of the map. See, this is 300 solar masses, 150 and 100. So it's much more important in the 300 solar mass that the model prefer than in the other upper masses. So this is the idea here is to show that there is some evidence that these kind of galaxies have very massive stars that should be taken into account in these models that traditionally they were ignored. This very popular model, BC03, they only cover, in the tracks that we use there only cover up to 100 solar mass. So here we can see the HR diagram in 3 different time step from 0 to 1.5. This is 0, 1.5 in red, 0 in blue. Here 1.6 in blue, and the rate also grown at 4.5, and then from 4.6 to 10 million years. So this is evolution in the isochrone space, plotted in luminosity versus temperature from 0 to 10 million years. And in the middle panel, what we show is the presence of IRyA stars. So we see these are not, they don't appear before 1.6 and they disappear after 4.6. So it's a very well defined time range. This is for the LMC metallicity. And in the bottom panels, we see the corresponding spectra, where the blue is for the youngest and the red is for the oldest. So we see here that the blue line has the contributions from the IRyA, which is already off here. And also it's very important that we know something about the star formation rate, because at these very young ages, stars may be still forming, right? It's very hard to think that the simple stellar population really stops so quickly, right? So in the top, we have the evolution of a simple stellar population at 2 million years, and in the bottom, if it is a constant star formation rate. So we can expect very different spectra in the UV range if we have different star formation rates. So one should have a feeling for this, or just a guess for what we are observing. Now I will talk about another application of the models using this flexibility into the libraries. What we did here is some people, especially Sebastián Sánchez, which is in my same university, but in Mexico City. He's very interested in the manga part of the SDSS. And they have this IFU spectra of many, many, many galaxies. But they wanted to derive the physical properties of these galaxies observed with the IFUs. But the standard models, they didn't work very well because they have different resolutions. So what we did is in collaboration with Alfredo Mejías, he did all the work essentially of, they took a spectra of stars in the same fields of the manga survey. There are many stellar spectra. So he classified using, I don't know, computer techniques and machine learning. He assigned properties for 22,000 of these stars. As you know, this is not feasible to do by hand or by eye. So with this library, we could use our models, the same tracks that we use for the CV19 models, but put together in the optical range this spectra using this is the kind of diagrams that Alfredo Mejia has in his papers, where he tests and the distribution of the log G, the metallicity, the temperature, and they convince themselves that statistically the machine learning classification of the stars are okay. So we apply with this all this machinery of Sebastián Sánchez and collaborators. We use the CV19 models with the manga stellar library to interpret the manga data. They have here, these are typical color redshift and color redshift diagrams for the galaxies that they have in the manga survey. And for details, you can see their paper. So the idea was for each of these points to derive something about the stellar properties of the galaxy using stars and models that are suited for exactly the same spectral resolution as the IFU data in manga. And so we see this, the black is the observation, the yellow is the manga model, the CV19 manga model, and the residuals are here at quite flat. I remind you that we are not including the emission lines in the models. That's why the residuals are high here. But we see that you can get very good fit to the spectra. And so they did, and they solved, they have an immense number of catalogs with the properties of these manga galaxies, studying each different, I mean, they have hundreds of diagrams like this in their publications. And you can see here, they can derive properties of the mass of the galaxy, metallicity, and essentially all is based in population synthesis suited for their needs using the correct library. As I said at the beginning, the tracks are very good, very stable. The problem is the spectra that you put on it. So if you want a specific set of data that you want to study, it's better to use as good as possible library to the problem you want to study. Another interesting application is this, the Megara instrument that is a project of the Universidad Complutense de Madrid and INAOE in Mexico that is in Canary Islands where Ignacio is. So they have a spectra of very high resolution. And as you know, our models don't work for that. So we are collaborating with Paula Coelho from Sao Paulo, which she computes stellar models of very high resolution that we use with our tracks or with another isochrones as well to try to study or to interpret the models or the spectra that people are getting with this instrument. One of the main observers for this Megara thing in the INAO is the Divakara Maya, who has been encouraging us to work on these models. As you know, because you already heard Paula Coelho in this series of models, she has a series of spectral models that we have used to compare with different libraries, and we have a paper on if it is better to use the syntactic or the empirical libraries. But what we are doing here is we are using a very high resolution version of her models to compute galaxy models with different isochrones. Here in the bottom panels, these are different isochrones of the VASTI data set for this iron over hydrogen. And you see that they differ a lot depending on different parameters. This is at 12 gigayears. This is not the important thing now is not what I want to show is that we can compute because we have the Paula spectra for all these possibilities. We can compute the spectra. And we get interesting things in which the residuals after they feed the spectra are quite good. Here and on top there is a model and the best fit is in red, you can barely see, and the spectra is in black and the residuals are in green. So you see you get very, very good agreement with these things. And again, the improvement is not the tracks because the tracks are the same, it's just using the correct stellar library. This is a typical spectra from these Coelho models. And you see it's very high resolution, it's no noise, it's real data. that we are using with Divacara and collaborators to study some star-forming regions in distant galaxies. This was also used to produce these index diagrams that people like Worthy introduced many years ago, but trying to use them as diagnostics for metallicity. This is a lot of future in this work. We have not explored completely because it's a still work in progress. Now, there are many challenges now, as you all know. James Webb is in operation and his work is producing data much more faster than we can think. So what we essentially, the models we have been tested for nearby populations. I mean, everything compared to James Webb is nearby. And so these models, we are not sure they will work for very distant universe. And eventually, some of the James Webb data, we may not have the right ingredients. So people have been looking at the local analogous galaxies to try to see if the very distant galaxies are similar to our local analogous, or what weakness we have in our current models, which is very much the same question that Sandage asked about 3C295 using M67 and NGC 188 60 years ago. The main motivation for this is work by Senchina, and these three other works I already talk about, but especially Senchina has drawn attention to the potential limitation of our state-of-the-art single models because they don't include very well the very massive stars. And he has you look at his web page, he has this kind of paragraph saying that. So he has some interesting papers which show that there is some evidence for an overabundance of very massive stars in nearby star-forming regions. Extreme nearby star-forming regions, he calls them. So this is like what he calls this is like a benchmark for stellar population synthesis models. See, what he stressed that as we observe higher redshift galaxies of lower mass, the interpretation of galaxy spectra depends increasingly upon models of very young and metal-poor stellar populations, which our models have been not, or current models have not been tested in this regime. He studied in detail 7 galaxies closer than 120 megaparsecs, in which there is no galaxies, star-forming regions essentially, which had very young stellar populations below 20 million years, and which show optical Wolf-Rayet stellar wind signals, which are ideal laboratories to test the SPS models. So in his papers, you can see these kind of diagrams. So he have the helium 1640 here, you can see in emission here. And he argues that the CV19 models have a good, more or less, they can reproduce the 1640 model, the 1640 line when we did all this improvement that we did for, essentially for him, we introduced the power model for the Wolf-Rayet stars and did a lot of work. But at the same time, he concludes that there are some discrepancies in the carbon pore lines that cannot be explained by current single star models, which you can see in this part of the plot. So the conclusion in this paper is that we need to include more massive stars, which one of the most likely progenitors is the mass exchange between binary stars. So as long as we don't have the binary stars in the models, we will always be lacking this kind of, or we will be lacking this kind of evolution, which this has been already addressed by BPAS people in IRyA and collaborator papers. But we wanted to do our own to keep it in the same format that people are used to do. So we started working in this project of introducing or building stellar population synthesis models in the Bruzual and Charlot style, using massive binary pairs of massive stars, which is what we are more interested. So we got together with many people. Essentially, Alessandro Brazan is the one that introduced us to the evolutionary tracks of these binary pairs. And the problem here is that there is no an initial malfunction for the binaries. So we have to sample this more or less stochastically, or assume an IMF for the primary stars and then use some statistical probability to have the binary stars. So in total, in summary, we have some work, which this year we have a paper with this student from Paris, Marie Lecroix, which we were able to use models in which binaries are evolved to compute some interesting physical properties. I will go a little bit in detail about these models to see what happens. Here we see this is the HR diagram. Essentially, we are seeing it's the same diagram, but in highlighting different aspects. This is 1 million years, it's very early, and the top panel shows the primary stars, the bottom panel, the secondary stars, just essentially at birth. And the color bar here is the mass, so you can see here the mass. And here I think what we will be showing is different type of stars, and the same here. But I will show how this evolves. Then you can see them when you see the presentation in YouTube. You can see it in detail because I will go a little bit fast. So essentially, this will get very complicated as we go in time because there is mass exchange between primary and secondary. So 2 million years, we start already getting some messy things. In 3 million years, the primaries are evolving. You see that the evolution is different from the primaries than from the secondaries. At 4 million years is quite different. 5 million years, it gets messy. 6, 7, 8, 9, 10, 20 million years, 30, 40, 45, 50. So the idea is that we want to use our experience modeling the spectra of this, because the Bressan and collaborators, they give us the tracks, right? They tell us, well, this is what happened to the binary pairs as a function of time and the mass. And so just get these tracks and put a spectra on top. So it was a big challenge, but it worked out. Also, from these plots, we have interesting things like the Wolf-Rayet star distribution. Here you see for this metallicity, there are no Wolf-Rayet in a single star. So because we have columns, the first, third, and fifth columns are binaries, and the second, fourth, and sixth are for single stars. We can see here the distribution of Wolf-Rayet stars in the binary model at this metallicity as a function of mass. So we can see at 1.9 million years, they will be very important. Right? As we go to other metallicities, we can see in blue again, these binaries, in red is a single, so they are quite different. again, 0.08. There are many ages, regimes in which we don't have IRyA stars in a single star population, but we will have it in the binary star population. So that's interesting and important. Also, the very massive stars, the blue is the binaries, in red is the single stars for the same metallicity and same ages. We see that it's quite different. In the single star, we will never go about 300, and here we go up to 500 just because of the mass exchange. They start at the same range, and in the binary, at the beginning, we don't go very high, but then they start exchanging mass, and that's what happens. So what happens? We have all this information. We have to put a spectrum. Again, I have here the binaries compared with the single stellar spectra at different ages for different stellar groups. And we can see that in the single stellar populations, we have very little variation. Right? It's almost, at the ages, we only have the sun white dwarf and the normal stars we call, which contributes. We have essentially two components, where in the binary stars, we have contributions from the world riots, and we call very hot stars also, which is very massive stars, essentially. So you see that the internal ingredients of the stellar population is very different of the spectra. You can see here also that if you compare this spectra with this one, is quite different in the ultraviolet, which is essentially what we wanted to get. Very different, much more emission in ultraviolet when you include binaries than when you don't include. This is for this metallicity. We can do this for many metallicities. At the moment, we have essentially the same metallicities implemented in single and binary stars. So one of the first things that people are interested in is the number of ionizing photons. This is pure binaries. Take a model with no single star, just pure binaries, so we can compute. This is the number of hydrogen ionizing photons or helium ionizing photons for different metallicities and pure binaries. Helium-2 ionizing photons. These are not normalized to anything. Just we take 1 million binary pairs and compute the number of ionizing photons. Then we can mix a model in which we have a fraction of binaries plus a fraction of single stars and compute the same thing. To make it more elegant, we have it now normalized to 1 solar mass, which is the same normalization that we use in the BC models. And the nice thing, what you can see here is the binary fraction. The black dashed line is a pure single stars, and the top line is a pure binaries. So we can see how the ionizing photons, the hydrogen ionizing photons or alignment photons increase as a function of time with the binary fraction, which is a nice result. This is essentially the big difference between 10 million years and 100 million years here. Now we have the models going all the way to 14 gigayears. It's more extreme for helium-1 ionizing photons. So it's a huge difference between single star models and models with binaries. Even you don't have to go to full pure binaries, even in this range, around 30%, 40% binary fraction, and still you get a big increase. And it's even worse for the helium-2. So the single star models will never explain or produce any helium-2 ionizing photons, whereas the binaries will do. Just because you can see that since you are producing massive stars due to mass exchange, you can reach the same levels that you have at the beginning when the population was reached in massive stars. That's the only, it's like having a star formation rate that is continuous in a way because you are replenishing the massive stars that were disappearing with evolution. So this was used by Marie in her papers to compute several properties of this, the nebular emission from these kind of populations. She compares our models also with the BPAS. We call our models GAL7 because the combination of our GALAX-F model with the 7 models, which is what Bressan and collaborators compute for the binary stars. So this will be available for people to use in the short time. We have to remember that here is not so simple to have a single IMF or whatever is always stochastic, the way we sample the binary. So, but I think it will be useful for people. This is the kind of diagnostic diagrams that Marie computed with using this model. So you can see here color coded by metallicity and age, and her paper is full of these diagrams if you are interested in this business. Also, we have the spectral evolution of the stellar populations using the binary stars. I want to show you a little bit. Here, what we have is 4 different metallicities at 1 million year, and the binary fraction is color coded as shown in the color bar. So I will, if I go, well, the age will be increasing, and you see that in the ultraviolet, you will have it will be spreading the amount of flux here, essentially because we have the binary stars contributing to this light, and it happens at different ages, at different metallicities. As you see, at 2.7 million years, is almost in all metallicities, we will have a wide range of possibilities in the UV, depending on the amount of binaries that we have in the spectra. So it's interesting, even if maybe it's just a textbook exercise, well, it's pretty. 10 million years, 15 million years, even 18 million years, 20, 50, 60. But we have all this information. So the important thing is that at least we have some handle on this now, and we can, in the past, people will always say, but you don't include binaries. And they say, no, we don't include binaries. So now we can at least have an idea of what happens if we do include binaries in our models. So I would like to conclude with these statements. I think that considerable progress in evolutionary tracks and spectral libraries has been taking place in the last few 10, 20 years, which have allowed us to build better models. The prospects are very good or good for both in the ultraviolet and near infrared ends. I didn't mention it, but we are working also in improving the infrared part of the spectra to have the patient lines with a good profile and all these things. The observation have allowed us to calibrate and understand much better the SPS models. The Bayesian techniques at work for galaxy data analysis have been used very successfully, both for stars and spectral fitting. The model seems useful to estimate the interstellar physical parameters from the rest frame UV emission line properties of distant galaxies. And combining these models with the codes like Cloudy allow us to estimate the interstellar metal abundance at very far from solar or slightly subsolar metallicities, or even in primeval galaxies. Also, the stochastic fluctuations, which I didn't show, because even for single stellar population, if the mass is not very high, you can have stochastic fluctuations in the number of stars, which will produce some fluctuations in the property of the models. And also the binary stars produce very important difference in standard SPS models. So I think it's mandatory to include a good treatment of massive binary stellar evolution that we are doing at the moment. Well, thank you very much. I'll be happy to answer questions from you.
Thanks so much, Gustavo. Really nice talk. Lots of very interesting ideas to think about. So we have a bit of time for some questions. So if you want, you should raise your hand or open the mic. I mean, while there's this, I was wondering, so you were mentioning stochasticity, and in these types of really complicated problems of very young populations with very massive stars, of course, stochasticity, the shape of the slope of the IMF at the massive end, that can also bring degeneracy. So just playing devil's advocate, could you be in a situation where your results could be somehow degenerate? So you may think that you need lots of binary stars when you don't need so many, and then you just simply need to change the slope, or the M up that you mentioned, like 300 solar masses. How degenerate is that?
No, as you know, it's very degenerate. So, I mean, you can always cook a model without binaries that will behave the same as binaries. But, you know, we would like to have the two possibilities at least. But it's true. I don't know. It's a matter of faith. If you rather think there are binaries or very strange IMF.
With stellar populations, it's always that, but it's a very interesting idea, because when at some point in your talk, when you were mentioning this, for instance, the treatment of low metallicity stars, that we don't know them because we don't have local analogs. It's actually very interesting, because we are in exactly the same situation many years ago with massive ellipticals, where you have a large number of stars at very high metallicity. And how many of those in the let's say in the Milky Way neighborhood are the types of high metallicity stars we are expecting to find in massive ellipticals? Not many. So it's another leap of faith that we need to do. I mean, don't you think that there's an analogy in a way?
Yeah, it's very analogous. So I think what we should really do, because now we have all the tools, is to have models with binaries or with very top heavy or bottom heavy IMF, and not that people choose, but just try to see if we can say something about this. I guess the evolutionary rates are different if it's just the IMF or just the binary. So eventually, with all this wonderful data that is coming out of James Webb, maybe we can put some serious constraint on what's better. That will be interesting to analyze.
And when you were along these lines, when you were discussing, for instance, the number of ionizing photons, that in binary populations they actually can be substantially different with respect to the single stars.
Yes.
Any thoughts on the way, for instance, the calibrations that we normally make when we transform H alpha luminosity into star formation rates? Could that be severely affected in this case, or?
I think so, because I mean, when people do this calibration, somehow they assume something about the stellar population. Most
So
likely, if you
have
assume a pure binary, will get different chemical law than if you use a pure single. Right? So that's another big error bar.
So any questions so far?
People do what they can.
Yeah, sorry. Please go ahead.
People do what they have available at the moment. So I think
True.
we will have, when this tool is available, I mean, people can do some serious comparisons. Because
I mean, I guess the killer type of observation would be, at some point, could you actually devise an observation in which we can actually falsify the presence of a single star stellar population rather than a binary stellar population? Can we actually simply rule out the use of a more traditional one? So is there an indicator? I think that would be an interesting thing to.
Yeah, once we have the models, I mean, we already have it, but we haven't had the time, or people like you maybe are more suited to find these contradictions. But you will get them.
Oh, well, I'm not going to hog all the space because it's a really nice talk. I have lots of questions, so offline I will ask you at some point. It's really
Sure.
very interesting work and lots of interesting good things. So I
Thank
don't know if the other people don't have any questions. I guess we can stop now. But so I will really thanks so much, Gustavo. That was
Okay.
a really nice talk,
Thank you
and
for
it's
inviting
going to
me.
be YouTube.
Yeah,
It
sure.
will be
And
in
we
YouTube for
keep in
people to
touch.
enjoy.
You have good ideas to how to explode these models. Because I mean,
That's
you know
great.
that building the model is a lot of work, and then you spend
A
months and
huge
months and
amount of work.
months and months. And, oh, here is a model, and you are
Yeah.
out of energy to do any test
Yeah.
with it. Okay.
Anyway, so thanks so much, Gustavo.
Thanks
Take
Okay.
very
care.
much,
Bye.
Gustavo.
Bye
Yeah,
bye.
bye.